thank you very much for giving us the opportunity to present here tonight. So Adrok is a technology company. We're based in Edinburgh in Scotland, and we've developed a new way of looking deep into the ground in an environmentally friendly and conscious way to find minerals deep in the ground. So the motivation for doing this was twofold. Mining companies were asking for ways of looking deeper into the ground in the subsurface. So we knew that radio waves with its long wavelength can go deep into objects and can identify things and identify depth very well because it's got high definition, high resolution capability. And secondly, because of the economics, I mean, the demand and supply metrics of the industry. There was a huge demand for metals. I mean, copper, especially nickel, etc., gold. And the supply, I mean, the supply, if you look at the depth down this column and through time, I mean, the shallow stuff, the easy stuff has now been found. It's becoming more difficult to find the easy stuff. So the mining explorers have to go deeper into the ground to try and find the minerals. So atomic dielectric resonance is the name we gave to our technology. So we transmit radio waves into the ground. We measure the dielectrics and the conductivity. Those are the two rock properties we measure of the subsurface. Different materials have different dielectrics. Air has a low dielectric of 1. Gabbro, for example, has 5 to 10. Water is higher, it's got 80 in dielectric, and it's more conductive as well. And we measure in the time domain and also the frequency domain. The time domain, we timestamp every single transmission that we pulse repetitively into the ground. And we can timestamp the returns as well, measuring the time it takes for the signal to come back to the receiver. And the frequencies we operate is between 1 and 70 megahertz in frequency range. So we send all those broad band of frequencies into the ground at the same time. These are the sort of ranges that ground penetrating radar similarly use as well. However, ground penetrating radar only sends one single frequency into the ground at one time. So the advantage of having a range of frequencies, we can send certain frequencies deeper into the ground, and these are the lower frequencies that go deeper into the ground, and the higher frequencies go shallower as well. So we can use different ranges through the ground. And in terms of other geophysics, we have borrowed principles from seismic technology. So we are a reflection technique. So wherever we get a change in rock type or contrast in rock type, we get a bounce back, a reflection from the subsurface. So the system itself is very small and portable and lightweight. We only need 2 or 3 people to physically move the equipment across the ground. And if we had enough money, we'd buy a Boston Dynamic dog, a robot dog, and use that instead of the humans. But alas, we are where we are. So we use low power as well, so we transmit milliwatts of power into the ground, and that's one of the secrets to getting better penetration through the ground. So we use less power than the light bulb above my head here that we shine into the ground. So the lower the power, the better penetration. Ground penetrating radar uses megawatts of power, so it's very high power, so it totally splats or saturates the near surface of the ground, and it doesn't get very much penetration through the ground because of that. You get nice pictures of the shallow near surface, but not the deep stuff, which is what we chase using our technique. We use 4 rechargeable lithium-ion batteries, so we're self-contained with our power in the ground, and we can run the system 24 hours a day in the field if we need to. So yeah, as I mentioned, we are environmentally friendly. We are also one of the world's only geoscience companies that is working towards B Corporation certificate. Just now, which we're almost there getting it. We have very low carbon footprint. We use low power. We use rechargeable batteries. I mean, the only carbon that we produce is from the flights that we take around the planet, but we often offset that with other ways. in the carbon chain. So we are also environmentally in terms of applications as well. I mean, we are in the minerals space, we all are in the oil and gas space, but we're also in the renewables space. We look for sources of natural heat in the ground for geothermal. We look for water, and water is very important for mining operations as well. So I mean, having a nearby supply of water is important. So looking for aquifers deep in the ground is important. And we can also find the future metals as well. I mean, the lithium, the uranium, etc. These are and potassium as well for the potash industry as well. For agriculture is another environmental one. So back to the technology. In terms of the technology, we always get asked, "Oh, how deep can we go? Radio waves can't travel deep into the ground," and that's typically just a legacy from people using ground penetrating radar, which is designed to go shallow. So we teamed up with Tech a few years ago. I mean, Tech subsequently became a shareholder in their company and a supportive investor. So we went to one of their mines in Washington State in America, and we went to this mine called Portability. We went underground, we pointed our transmitter vertically upwards and through the ground, and we set up a test, a real world test of going through solid rock, water and air. So rock, water, air, the three basic materials of the planet, and to see how far we can go and can we get a ping back from the surface. So from the dielectrics started off with 1 inside the mine because it's air, and then we went through rock, which is between 5 and 15 in dielectrics. There's a limestone material that we went through, and then we hit the water body at the top, this riverbed, and the dielectrics pinged right up off the scale to 80, high change in contrast from the rock. And then as we went through the water, we settled back down to air, and we shot out into air, and we stopped collecting data at that point, although I'm sure we could have gone further up into space. So the dielectrics showed empirically that we collected data through these solid objects. And this was also corroborated by our energy the pulse as well, which shows the different changes in the mediums. So and bear in mind as well, this is us sending the waves two ways. So we've got to send the wave 360 meters up into the air and then back again. So effectively we're doing double that. So it's 720 meters through the depth channel. And then also water as well, because it's high dielectric at 80, it's actually simulating an even greater depth. So I mean, we're effectively going through 1,000 meters odd of rock material. So because we're empirical scientists, we collected the data, we played around with the data, and we produced this video. So we've got the dielectric measurements, which we took from the ground in blue here, and we've got our pulse, which we forward modeled and then inverted and produced this video showing what actually happened to the pulse. So the pulse starts off with a nice high amplitude, nice standing wave, which goes through this constant rock material, and it doesn't really change that much through the rock column, and then wham, bam, it hits the water, and you get this big reflection back from the water. So you get the first reflection here, the second, and you get multiple reflections back coming up the channel back to the receiver. So unequivocal evidence that we went through 350 meters of solid material from underground. Now, as I mentioned, ground penetrating radar can produce images of the subsurface and can find sulfides, but the depth of penetration is very limited, so it's only 10 or 20 meters that you can go. So one of our clients who worked in Charters Towers is a company called City Gold, and they use this a radar company to collect the data, but they were sorely disappointed because they could only go through 10 meters of the subsurface. Now the ground penetrating radar, I mean, other companies have purported to measure sulfides through the ground. I mean, albeit just a few tens of meters through the ground. But using the dielectrics, you can differentiate between sulfides. So we get a nice dielectric of 30 for sulfides because it's high conductivity, which is interesting. And other researchers have published papers on finding sulfides. Hammonds and Sprank found that they could see sulfides through subglacial material, through sort of permafrost material, which was interesting. And they published that back in the 90s. And only a few years ago, the Mars-SIS project, which is the satellite orbiting the Mars and monitoring the polar ice caps in Mars, they published results showing that they went through several kilometers of Mars material, which is great. Again, using a radar radio wave from satellite. So we are like GPR in the sense that we get this sort of amplitude stretch of the reflected energy back, but the big difference is that we can go a lot deeper than ground penetrating radar. I mean, we can go thousands of meters through the ground as opposed to tens of meters through the ground. So the reflected energy, we've set up various tests. We've done some work with City Gold in Queensland and Charters Towers. We've also done some work here in the UK with Strongbow Exploration in partnership with Cornish Lithium. And from the energy responses, you can get good indications of mineralizations. So that the higher the energy, the bigger the peak here on our measurements, the coincidence with the mineralization is stronger. So this is a drilled results from Charters Towers showing that we were spot on in the ballpark with detecting where the minerals were and the subsurface ahead of drilling. I mean, they drilled based on our results. So can we find disseminated sulfides? We've done massive sulfides. Can we do disseminated sulfides? So I mean, the trick is, can we fingerprint the difference? So we need to set up a method, which we have done, which fingerprints the sulfides. So we've done that using spectroscopy. So we know that our sinusoidal waves that we put into the ground, they've got energy, they've got frequency. So from that, you can make a spectral measurements, a spectral classification of the subsurface. And you can use that to start constraining the target area and the depth at which the mineralizations occur, and you can start planning your drilling and your drill plans based on our results. So the energy and frequency results, these squiggly lines, which look a bit messy, but they are containing lots of detailed information if you stretch it out, because this is 1,000 meters and we're just presenting on an A4 PowerPoint page here. But you can, even from this, you can see that these spikes are coincident with the mineralization in this zone here. So you can start assessing and pulling out the data and start fingerprinting and setting up control measurements and control boundaries and boundary conditions for the different materials. And you can also adjust the depth as well. You can do plus or minus 10 meters, 50 meters, etc., up and down the depth scale to classify the materials if you need to do that. And we've also demonstrated that this is a very simple, repeatable, and client-friendly method. We've done this on repeated sites on the same project and also in different projects around the world using this methodology for targeting sulfides. And again, you can set the confidence layers. You can actually start grading the mineralization based on this technique as well. So, I mean, one case study that we did, this was in Ireland, and they were looking for sphalerite lead zinc materials. So going down sort of 600 meters, 700 meters, 1,000 meters there through the ground. I mean, the key information was around about 350 meters through this farmland in the countryside of Ireland. We did find some deeper targets, but their drilling, the training drilling didn't go as deep as that, and their subsequent drilling program didn't go as deep as that. So, but yeah, I mean, again, another good result. We were spot on with our zones of mineralization. And we also classified it purely for the different zincs as well on the same site. And I mean, this was at 350 meters below the ground. A bit deeper, we went to 500 meters in some locations. And again, this is the same projects in Ireland. I mean, we went through the Walstortian limestones into the sulfide-bearing breccias, and then we found the basement as well. We had a big energy spike in the change from the breccias to the lower argillaceous limestone in the basement. So yeah, so we can produce all these lovely models. I mean, these are a good distance away from each other, these two but we can still classify and outstep from our virtual drill locations. So the results we send to the clients, we try and make it very simple. It's just X, Y, Z information. X marks the spot, go drill here. Basically, that's what we tell the clients. And we've used this in many case studies around the world, and we've had some great success stories with this. I mean, these results look good for correlation, and hopefully our clients are going to drill on this and give us some ground truthing on the back of this. Another project in Australia, this is in Adelaide. This is the DET CRC organisation, this research body that was testing out lots of different new technologies. We were invited down to test our new technology. It was a great field laboratory for us because it had lots of different measurements. It had seismic, it had downhole tool measurements, it had borehole data, it had core samples, it had everything. So it was great. We were like kids in a sweetie shop with this project. So the 2D section at the back was our measurements, our seismic equivalent measurements that we produced. And we had vertical scans, we had angled scans through the site. And the end result which we produced in a 3D model was spectacular. I mean, we had great match up in ground truthing versus the physical drill locations, which was great. And we demonstrated that there was clear dipping west-east bed throughout the section as well. And our imaging was very comparable to the seismic imaging. We picked out the main horizon indicators, and we picked out lots of faulting and fracturing as well. So in summary, I mean, our mineralization exploration technique based on radio waves can go deep into the ground. We've demonstrated that we've gone to 1,000 meters in many different cases. We've produced a sulfide fingerprint technique, and we've managed to target the grade as well, so we can differentiate the grade of the sulfides that we find as well. And yeah, through lockdown, we've been working on these legacy projects. We've been doing internal blind tests with our staff as well as they've been training on the data, and it's been a real joy to work on this project. And we're very confident that what we've produced represents a major step forward in the use of deep penetrating radar for the identification of sulfide targets prior to drilling. So I mean, using our technique to guide the miners where to drill next and where they should go in their exploration path is a major feat. And of course, we do this environmentally friendly. We have very low carbon impact, carbon footprint on the planet, so we're saving the world with our technique. We've got many case studies, so if you want any further examples of what we've done, we've produced lots of different case studies over the years. I mean, we launched our service in 2007, so we've been at this a number of years commercially. But even still, I mean, since we've launched the products, we've suffered from skepticism, which is only natural. People think this is too good to be true, etc., etc. So we basically put our money where our mouth is, and we've luckily been through two big rounds of funding through the company, and we've had supportive shareholders who support us in doing these experiments and doing these case studies. So we've gone out, so we've taken measurements, trained on the areas, and produced amazing results. So we've got really good ground truth and corroboration and technical papers on what we've done. And finally, just a bit of humour, there's a major football event on tonight here in Scotland. So I mean, Scotland are just about to qualify for a major tournament for the first time in 20 odd years. So hopefully we'll win. But yeah, I mean, during this pandemic, we've been using our time very wisely, going through legacy data, perfecting the sulfide mineralization tool. And we think we've smashed it out of the park. We think we've done an amazing job with this. And I think other geophysics companies are going to be hard pushed to catch up. I mean, some geophysics are very good for producing images of structures in the subsurface, but I mean, pinpointing the mineralization is the key. And we've definitely done that. So we've demonstrated that repeatedly that we can do that. So thank you very much for your time, and I hope you enjoyed that. And if you've got any further questions, I mean, please feel free to reach out to me outside this event. Thank you.